Hello. Thank you everyone for being here with us at the last briefing session. The title of our talk today is Quack, Hindering Deserialization Attacks via Static Typing. So let's start off with some introductions. I'm Neo. I'm a PhD student at Brown University. I do research in system security, including program analysis, speculative execution attacks, and more. And I'm presenting today with Andreas.
Hi, I'm Andreas. I'm a PhD student at Columbia University. And like Neo, my research applies program analysis techniques to solve security problems. And this presentation today will be an example of that. But this work was done collaboratively with Yaniv, who led this work but can't be here today, and our advisors Vasilis and Jufeng. So over the years, we've seen numerous talks about the dangers of deserialization within our applications and passing untrusted inputs to them. But what we'll notice is that many of the talks, with few exceptions, are about attacks. And our defensive advice tends to be a warning to developers not to do this, resulting in CVEs over the years regardless. And so we set out to design a mitigation that can be applied as a defense in depth to help prevent the exploitation of these attacks. And this resulted in a system that we called Quack, specifically implemented to solve this problem in PHP applications, which we'll use throughout this presentation. And it was published in an academic venue called NDSS. And so the goals for our talk today are to, one, introduce Quack to the security community and try to help it escape the lab and be put to more practical uses. And two, just continue to raise awareness about the risks of deserialization attacks and hopefully give you a new way of thinking about how they might be mitigated and defended. So to get into the details of what Quack is and how it works, we'll begin with some background on how these PHP deserialization attacks work. And then we'll get into Quack and we'll describe how it uses static program analysis techniques to harden applications against these attacks. And then we'll end with some takeaways about where Quack can go and the future of deserialization exploits.
Cool. So let's start off with the exploits. So most people here have probably at least heard about deserialization vulnerabilities. They're still a pretty common type of vulnerability, multiple CVEs issued every year. These are just some recent examples of PHP deserialization vulnerabilities, which is what Quack is concerned with. So PHP provides this function called unserialized, takes in a string representing a serialized object, and then it just reconstructs the object and returns it back to the running program. And as you can see at the bottom, there's a big red warning that at some point says that a malicious user may be able to exploit this. So let's assume we have a PHP application, has a call to unserialize somewhere, and the input to it comes, it's untrusted data coming from the user. And let's say that when the programmer wrote this application, they expected this call to unserialize to return an object of this class called app. And this would look something like this. So at the top, you can see what the input string would look like. You don't need to worry about the exact syntax of it. The important part is that it encodes information about the type of the object and its properties. So when this runs with this input, it would create something like the object at the bottom. So it would be of type app and with one property with the value myweb app. However, if this input is controlled by the attacker, they can first of all change the properties of the deserialized object. So for example, they could just change the value to some different value. But beyond that, they control the whole type of the deserialized object. So instead of deserializing the type of the object that the developer intended, they can just make the app deserialize a completely different type. And they can even go a step beyond that, and they can actually cause it to deserialize a whole object hierarchy consisting of nested objects by just setting the properties of other objects to new objects. So they can deserialize a bunch of different objects. However, their actual goal is not to just deserialize and inject random objects in the runtime. They want to actually divert control flow and execute something malicious. So let's see how the ability of injecting arbitrary objects allows them to do that.
So continuing with this application that Neo's introduced, imagine that it also has a class shown on the screen named command executor, which has two very, very convenient properties for an attacker. One, it has a method that directly overlaps with a method that's called on the deserialized object. And two, it has a trivially malicious implementation such that an attacker that controls the command property of this object invokes system on these objects. And so when an attacker provides a string like this, the attacker achieves their goal of invoking some new method that the programmer did not intend and executing some malicious functionality. But this is quite a contrived example and trivially exploitable if it exists in the application. So making this one step more realistic, imagine that this run method doesn't exist. There's no direct overlap with something that is invoked on the deserialized object. What is the attacker to do? Well, PHP has a feature named magic methods, which are methods that begin with a double underscore and have special purposes that are automatically invoked in certain circumstances. In this case, the wake up method is invoked automatically when an object that invokes this method is deserialized. And other such useful magic methods will be called when the object is destroyed or when it's converted to a string. And so these are useful for an attacker to identify locations and events and invoke new methods. But still, this class has a pretty trivially useful for an attacker implementation of this magic method that probably won't exist in a real application. And so making this, again, one step more realistic, what we are more likely to see are classes that implement these magic methods but with some more realistic implementation that doesn't directly hand an attacker the ability to implement calls to system. So what is an attacker to do in this scenario, and how does the PHP deserialization exploit proceed from here? The technique that's been used for years is called property-oriented programming, or POP. And the general idea here is that the attacker will instantiate or create a string that, when deserialized, creates some top-level object that is strategically chosen because it has a magic method that will begin executing as the attacker needs it to. And then the attacker will nest objects within the properties of this top-level object that are chosen such that their methods are executed in sequence after the initial top-level magic method is. And this kicks off a chain of attacker-chosen functions that will eventually reach a malicious function of the attacker's choosing. And this is a high-level explanation. I'm about to illustrate it with an example. So if this, if it's not clicking right now, don't worry. But we've known about this technique since at least 2010 in a Black Hat talk by Stefan Esser. So again, just to illustrate this, we've taken some classes from an application with a known, or with a real CVE that is exploitable with a deserialization attack. And we'll step through an example of how this pop chain would work. And so each box here represents a class within, or a small subset of classes within this application. And within one of them, there is a method that has a vulnerable call to unserialize. The programmer really only intended for one class to be deserialized at this program point, and that's this program highlighted on the screen. And every other class within the application should not be represented in the serialized string. But the attacker is able to recognize that there's another class within the application that has a useful method for them. It's this method named current. And within the implementation of this method, it invokes some callback that the attacker could potentially set for themselves with some argument that the attacker can control as well. The problem here is that this current method isn't directly invocable by the attacker. It's not a magic method, and there isn't a convenient invocation of current on the deserialized object. So the attacker's question is, how do I invoke that method? And what they do is they'll strategically identify some other classes within the application and create a serialized string that encodes one of these classes that has a magic method, like this lock class that has a destruct, and then set the properties of that initial object to objects of types of these other classes, and invoke the methods of those classes through the deserialization process after that destruct is invoked, eventually reaching the current method with attacker controlled values, invoking a callback, here that system with the command of the attacker's choosing. And so the key takeaway here is not necessarily how this works, but that the attacker is able to pull off this attack by having access to more classes than the programmer intended to be instantiated at this deserialization point.
Cool. So now let's go and take a look at what Andreas just explained, but let's see it in an actual demo. So what Andreas just described is a slightly simplified version of an exploit for a real CVE against an application called Moodle. It's basically like an e-learning platform. And it contains this snippet. As you can see, there's a call to unserialize. And this is the vulnerable part. And basically, it's in a part of the code base where a user can upload an XML, and then a field of that XML is a serialized object that's going to get passed to this unserialized call. So let's see how that's going to work. So, sorry. So first, let's take a look at the actual XML that contains the exploit. It's very similar to what Andreas showed. It's slightly more complicated. There's just a few more classes, but the basic idea of how it works is the same. And as you can see, the attacker has set the callback to be called to system, and then the arguments to it, they're gonna just echo something nice. So we have a running instance of the Moodle application. So the way, like the vulnerability is in a part of the code where the user can upload a quiz. So we just select the vulnerable format and then upload the XML file we just looked at. And now when we click import, the exploit chain Andreas described should run. And if it runs successfully, we should see something printed on the screen. And it did, as you can see, the exploit runs successfully, and it printed a nice logo. So we've seen how the attacks work, how the vulnerabilities work. So now let's talk about mitigations. There's a few different ways, recommended ways to mitigate these types of attacks. First one is to just not use unserialized and instead use a simple representation like JSON to store your data. And this can work pretty well, but it only works if you want to store simple data like arrays and primitive types. And it doesn't really work very well if you actually want to store complex PHP objects. Another recommendation is to ensure the integrity of the serialized data using cryptographic caches. Again, this can be a good solution if the application itself produces the data. However, again, that's not always the case. And the last recommendation actually is provided by the unserialized function itself. And it's an optional argument you can pass to it called allowed classes. And the way it works is it takes in a list of class names. And when that specific call to unserialize happens, PHP will only deserialize objects if they're instances of one of these classes that were provided to allowed classes. And if it encounters a different object, it's just going to replace it with a dummy object that has no methods and no properties. So if we go back to our earlier example, where we assume the developer wanted to only deserialize an object of the app class, this time they provide the allowed class argument, and they set the list to only that class. So the attacker's input that was trying to deserialize a different type of object is not going to get instantiated anymore. So their exploit is not going to work because no method calls will happen. And in this specific instance, eventually the application will crash because there's going to be a method invocation on it, like the run method, which doesn't exist on the dummy object that was created. But still, the attacker's exploit is going to be prevented. Now, unfortunately, even though this mitigation works pretty well, as long as you provide a small set with only the classes you wanted to deserialize, It's not really used very much. We found that only around 0.1% of calls to unserialize in GitHub repositories even use this argument. There's probably two main reasons why. First of all, developers probably are just not aware of the dangers of deserialization and how they can be exploited. The second reason is that it's probably pretty tedious to manually go through your code, go through every single call to unserialize and figure out what classes you actually meant to deserialize. Especially if you've already written your application and you weren't aware of this, it's very hard to go back and figure out what you meant to do. So there's two main takeaways we want you to remember from all this. First is that these types of vulnerabilities are exploitable because attackers have access to and can create objects of more classes than what the developer actually intended. And second, that there are some mitigations, but they either don't always apply or are not really used very much.
OK, so let's get into what Quack is and how it works. And we'll begin with its overall design goal. So after studying how these attacks work and the existing landscape of mitigations for them, what we decided was that if we could build a system that could automatically infer that programmers' intent for the classes that should be allowed to be deserialized at a given point, we'd be able to restrict the application using that allowed classes argument to break these exploits that attackers are using in pop chains. Now, inferring a programmer's intent perfectly is a challenging to impossible task. But what we do instead is try to use program analysis techniques to learn about what this programmer may have intended through the way the deserialized object is used. So at a high level, what Quack does is, given an application with some set of classes declared within it, it first determines a set of the available classes that are loaded at that deserialization point or could be loaded. Intuitively, this is effectively the classes that are included in all the files that are part of an include statement within the points in the program that this unserialize is invoked. It's a bit more complicated than that because of the dynamic nature of loading in PHP, but that's the idea. Then Quack will statically analyze the program and observe how the deserialized object is used within the program to infer a set of possible classes that the programmer may have intended the object to represent. And then Quack will take the intersection of those two sets, leaving just a set of the classes that are candidates to be passed as allowed classes to restrict the behavior of that unserialized call. And as a system, Quack looks like this. You input the PHP application source code. It analyzes it in two passes to create these two sets, and it will output a set that can be passed as allowed classes. And as an implementation detail, Quack is built on the Journ static program analysis framework, which, if anyone in the audience does program analysis, you may be familiar with.
Now let's look at some details about how Quack actually works. So as we mentioned, the first thing Quack needs to do is identify the set of available classes at each unserialized call. By available, we mean the classes that can be imported at that specific point in the program. So to do that, Quack starts by analyzing the file that includes the actual call to unserialize. It adds all the classes included in that file to the set of available classes. And then it visits all the files that are included by the current file, adds the classes defined in those to the set as well, and just continues doing that recursively until there are no more files to visit. After doing that, it goes back to the original file, and then it does the same process but backwards, meaning that it visits the files that themselves include the current file, and adds the classes that are defined in those to the set as well. And the intuition behind this last part is that we could have reached unserialized starting from any of these files, so we have to consider all the classes defined in these available as well. Class loading in PHP is slightly more complicated than this. There's something called autoloading, where class can be imported without explicitly being included in the file, but Quack takes that into consideration as well. So for the next component, Quack needs to figure out the possible types of the object based on how it's used in the code. To do that, it's based on a concept called duck typing, which is a concept in dynamic languages that basically says that an object is of a given type if it has the methods and properties that are required by that type. So in this simple example we have here, there's an object called animal, and there's two method invocations on it, swim and fly. And what duck typing tells us is that this animal object can only be used as a type duck, because duck is the only class here that actually defines both of these methods. So the way Quack works is it statically analyzes the source code of the application, sees how the object is being used, and it collects evidence about what its possible types are by using type inference rules that are based on this duck typing concept. So let's take a look at some examples of those rules. First, basically the example that we just saw. So in this case, Quack would look at the first use of the deserialized object. It would say that this can either be of type Quack or whale, because both of these classes define the swim method. Then it's going to take a look at the second use. It's going to see that only the duck class has the fly method. And because both of these uses were on the same variable, it's going to take the intersection of them, and it's going to say the only possible class that should be allowed to be deserialized here is the class duck. Quack also looks at property accesses on the object, same concept as before. Here it's going to look at the feather color property is accessed on the deserialized object. It's going to say that only the duck method has that, so these objects should be of type duck as well. Quack also looks at whether the object is being passed as an argument to function calls, and deduces the type of the object from that as well. So here, the object is being passed to that function, which has a type annotation. So Quack can just say this again is of type duck. If there was no type annotation, Quack would just continue looking at the code inside the body of the function and collect more evidence for the use of the object inside that as well. And our final example, Quack takes into consideration known PHP operators that indicate type information. For example, here it's going to see that the object is passed to the instance of operator, and it's going to say its type should be duck because that's a type on the other side of the operator. And these are just a few examples of our rules. We have a bunch more rules in the paper, which you can go check out if you're interested. Now, beyond just looking at the type of the outermost object, Quack also takes into consideration any possible nested objects that could be set as properties of other objects. So in this case here, Quack would look at the first two uses of the deserialized object. So there's gonna be a method call on it and a property access. So it's gonna say this object is of type human because that's the only class that defines this method and property. But then it's also gonna see that there's a method call on one of the object's properties. So it's going to collect more type information about the type of that property. So it's going to say that should be of type dog. So the final set of possible classes here contains both human and dog, because both of these need to be part of allowed classes when we call unserialized. Now, to put it all together, Quack has collected the set of available classes and the set of possible classes based on typing inference rules. It's just going to take their intersection and say that this is the final set of allowed classes. So we run Quack on the Moodle application we looked at earlier. As you can see, the serialized object is being used twice. There's two property accesses on it. So when we run Quack, this is part of its actual output. On the left, you can see the type evidence it has collected based on the type inference rules. There's one for each property access. As you can see, there's only one class that defines both of these properties. And that class is also part of the available classes set. So Quack will just set the allowed classes argument to only that one single class that contains both properties.
Okay, and so to see Quack defending this Moodle CVE in action, let's return to it. So here's the exploited instance. We'll reset it, and now we'll come and we'll take a look at this output that after analyzing this application, Quack has produced some output for us, which Neo has showed us. And it looks like this. It's a JSON file that tells us that within this application, there is a file that has a call to unserialize on line 93, whose type should be restricted to the qtype ddwtos underscore choice. And so we can take this type now, come into the running instance of this application, and we will go and modify that call to unserialize and update its allowed classes. And so let's do that. Hopefully I remember where we're going. Okay, on line 93, we'll see this vulnerable call to unserialize that Quack has identified. And we will add ourselves this allowed classes optional parameter. Now, you'll notice I'm manually making this change that Quack has recommended. We could also add a post-processing pass after the fact with Quack to analyze the AST and make these adjustments itself as well. Let me just make sure the parentheses are matching, and I think we're good. We'll save this.
You need to add class.
No, thank you. Yes. Okay, we'll get the class of that type. Save it. And now when we come back into our application, we will load the exact same exploit file. Sorry. Okay, and before, when the application was vulnerable, when this exploit file executes, it executes system, and we saw the ASCII art of the black hat logo. What we expect to see this time is for Quack to have prevented the execution of that system command, and the rest of the XML file will parse. And the functionality here is that it imports a quiz into this learning platform. And so we import, and we do not see that ASCII art print out. The exploit chain did not execute. And now we can learn from this quiz. Cool.
Cool. So let's close out with some takeaways. First of all, how effective is Quack? We evaluated Quack on 11 more applications other than the one we just looked at that had actual CVEs. And among them, they had 15 total vulnerable calls to unserialize. And we also ran an automated exploit generation tool that was able to generate the exploits for 5 of the CVEs. And then when running Quack and applying the allowed classes set that it deduced, we were able to block all methods for 12 out of these 15 vulnerable calls. What this translates to effectively is that there were no classes that should be allowed for these 12 calls. So the developer didn't actually even need to use unserialize. And overall, across all 15 calls, we're able to block 97% of the methods that the attacker had available to them. And the automated exploit generation tool was no longer able to generate any exploits for the 5 CVEs it used to be able to.
Okay, so how can Quack still be improved? Well, Quack's improvements, I think, fall into 2 broad categories. One is improvements to the correctness of its outputs. As with any program analysis tool, and especially those created as research prototypes to demonstrate an idea, there are some warts to smooth over. PHP is a large language with many features, and we don't necessarily know which features we still fail to accommodate. And so what we really hope from this talk is to build perhaps an interested community of folks who have problems and real PHP code that could be protected by this. And we'd love to get your feedback on, if you try this on code that you care about, does it work, does it not? Please raise some issues on our GitHub repository so we can identify those gaps in what we're in the implementation right now. And then this other category is usability. We would love to get to a point one day in an ideal deployment where Quack could be perhaps directly integrated into an IDE, such that as a developer is typing unserialize and using the object, Quack can make on-the-fly recommendations right at that point so that the developer locks down their application before it's deployed and has the opportunity to be exploited. And so where does this leave us with deserialization? Does Quack solve the problem entirely? What we've shown today is Quack can effectively restrict the number of classes available to an attacker in an exploit chain. What Quack is not designed to do and cannot do is prevent what we'll call data-only attacks, which would be one where the attacker can perfectly respect the classes of the intended programmer, but manipulate the properties in a way that violates security issues or has security issues. Simple example might be a user class that has a isAdmin property. And if an attacker creates an object of this and sets that isAdmin to true, that's clearly a security problem that Quack can't necessarily mitigate here. So Quack kind of joins a a set of mitigations for these types of attacks that has a use case, but leaves us with us still needing to be deliberate about what our use cases are when we write our applications. Is our use case one that an HMAC could apply to? Is it one where we can restrict the set of classes within that available to an attacker? And so again, just trying to add a defense in depth tool here to help manage these problems. I think another fair question is, so we've shown an implementation for PHP. Can this work for other languages? And while we didn't study the deserialization APIs of these other languages as closely as we did with PHP, our understanding is Java and C# have similar deserialization APIs that could allow Quack to, like the idea behind Quack to extend to. And in fact, at the exact same venue where we first published Quack, a very similar paper was published, kind of demonstrating this idea for Java applications. So I think there is some evidence there that we can extend there. But Python's pickle module in particular is notably much more expressive than what PHP provides. And so a Quack technique would not apply to a deserialization interface like that. So that concludes our presentation introducing Quack. What we've spoken about today are how these deserialization exploits work, and in particular pointing out that they tend to use more classes than the programmer intended. We've introduced Quack and shown how it works by trying to infer that programmer's intent to identify just the classes that are needed through the static program analysis techniques that we call static duck typing. And again, if nothing else, we hope to leave you, especially developers, with the reminder that you should always be deliberate about your calls to unserialize. And if you are using them, please think about using allowed classes, and Quack can help identify the classes to set in that policy. If you're interested, please check out our GitHub and further our paper. And we'll also be available for questions in the wrap room South Pacific D. Yeah, thank you for your time and your attention. And that's Quack. I guess I should also invite you to ask questions now, I believe, if you have any.
Hello. I had a question. It looks like you built it on like SML and OCaml's kind of type inference, but you took it way further with more modern static analysis. I'm not familiar with the latest and greatest, but is there some way you could do like a type checker that isn't actually enforced, where you just, I don't know, just something to make it restrict more classes of errors?
So the question, as I understand it, is like we have type checking from OCaml, and you know, like we have literature on how to do type checking well in these other languages. We've updated and implemented our own kind of type checking rules for this problem. Could we have done more to? I missed that last piece. Like,
Well, to have the program automatically figure out that there's certain types of transformations, deserializations that are just invalid, or that maybe you have to explicitly say, yes, I want to do this in the allowed classes or something like that.
again, like, correct me if I'm understanding this wrong, but like basically, could we add annotations in the program to like to provide some hints that like, yes, this is what I intend versus versus not?
To double check, just to get rid of some extra errors that might pop up.
Yeah, definitely. And Quack does so. So one of the challenges with like static analysis of PHP as a very dynamic language is like you can't soundly type check it the way that you can with like OCaml, right? Like it is an undecidable problem to do this perfectly, right? But PHP, like Python, has things like type annotations where you can, as a developer, basically say like, even though this is a dynamic language, this should be of this type, right? And just kind of leave these sprinkled throughout the code. And Quack does use these type annotations as hints within its analysis to infer that as well. So yeah, Quack is using that, and it really does help when developers do that. And thankfully, I think we are seeing more of that happening in like modern code bases, especially in the Python world, as people are adding type annotations two things. Yeah, it definitely does help. And yeah, Quack does use that.
Well, thanks. A great project.
Thank you. Great. Thank you.
Thank you, everyone.